Okay, hello everyone. I feel extremely honored and glad to have this opportunity and give you a talk about my research. I know right now is a very tough time around the world because of the virus, but the good thing is we still have this opportunity to share our ideas and information. So before my presentation, I hope everyone of you will keep healthy and safe. Okay, so uh, first of all, let me introduce myself. My name is Mingze Sun. I'm currently a PhD student at the University of Connecticut. My major is biomedical engineering. So the topic I'm going to talk about today is the effect of the mechanical property of the PEGDA hydrogel on polystyrene nanoparticles diffusion in virtual. So let's say a nanoparticle is a very promising tool to transport a molecule across the tissues. It has been studied in recent decades in biomedical engineering field. So there are a lot of different kinds of nanoparticles has been used. For example, like the polymer nanoparticle, gold nanoparticle, silicon nanoparticle, and the lipid nanoparticle, right? When we would like to evaluate the efficiency of the nanoparticle-based delivery system, we need a platform in virtual because the virtual platform is a real time and and it also allows us to do the transport analysis easier and quicker. For example, we can use the multicellular subfield to test the nanoparticle diffusion in this 3D tumor model. Also, we can use a hydrogel or any other kinds of or other kinds of different engineered tissue model. For example, like we can use the 3D printing technology to do the to mimic the tissue in tissue engineering. So there are a lot of different types of hydrogel have been used in biomedical application. For example, like the protein based hydrogel, such as collagen, fibrin, or some polysaccharide hydrogels, for example, like agarose alginate, right? So in my case, I use the therstatic hydrogels. Yeah, it is a kind of a PEG based hydrogel. So whatever any kind of hydrogel, it has the advantage or disadvantages, right? So for the reason why we choose the PGDA hydrogel is first of all because it is easy to do modification on the surface, right? And the other reason is tunable biomedical and we can easily change the physical properties. Um, so what kind of factors would change the, the hydrogen mechanical properties? Um, first, first of all, uh, it will be UV energy and photoinitiator concentration. So the mechanical property of the tissue is one of the main factors which could prevent the drug delivery um, from reaching the target area. So this is very important because if the delivery system cannot reach the desired site, it will dramatically decrease the efficiency of the drug. So uh, there's a lot of report uh, uh, related to the mechanical property of the hydrogel. For example, in this paper, we can see the hydrogel will have the different Young's modulus in different exposure time conditions. So this work gave us a very good a tip a hint that if we can characterize the mechanical property of the hydrogel, and also if we can find out the diffusion coefficient of the nanoparticles in hydrogel, uh, we can eventually, we will build up a relationship between the diffusion coefficient and mechanical property of the hydrogel. Then we can conclude that how the mechanical property of the hydrogel affect on the diffusion coefficient of the nanoparticle. So in my experiment or in my research, I tested different exposure time conditions on the hydrogel, and try to find out the nanoparticle diffusion in these different conditions, and then build up a relationship between the stiffness, the mechanical property, versus the diffusion, the nanoparticle diffusion efficiency. So the method I'm using uh, is uh, is quite straightforward. So I used a punching hole to get a hydrogel pillar with a diameter is 1.5 millimeter. The reason why I use this method is because in in the lab it's very difficult to track the nanoparticle diffusion uh, by using the optical microscopy. So usually, absolutely, we can use like confocal microscopy, but you know, if we can find a easier or cheaper way, that will be a good thing for the lab worker. So in this case, I ignore the confocal the microscope. So I would like to use the normal optical microscope. So I use the punching hole to get a pillar, and use a uniform cut to get a slice in the middle of the pillar. So you can see here. So I cut 2 times from here and here, and get only need the middle part to do the Florence diffusion analysis. And in this case, I use the 40 nanometers polystyrene nanoparticle, and it is absolutely fluorescent. And as I said, I use the fluorescence microscope to take the image for different timeline. For 30 nano, 30 minutes, 60 minutes, 90 minutes, and 120 minutes, right? And also I use the MATLAB and ImageG to analyze the imaging profile of the diffusion coefficient. So how can I get the profile of the diffusion coefficient of the nanoparticle? So I use the MATLAB to analyze the whole the whole image of the fluorescence imaging, and then I draw a circle based on the fluorescence area, and then starting from the central point, I draw a line, get, and then reach the edge of the circle, and then I did it as like of 360 times, and then I can scan the whole area of this Florence area, and then I can summarize the intensity at the same pixel position in each different lines, right? So if I can get a pixel value on this lines, I will, and then scan this area, I will have the profile of this Florence area. So for the mechanical property analysis part, um, I use a customized force sensor, and and the equation is widely used in physical field. So it's just an elastic modulus function. So the only different thing is I do not use um, the pillar in this case. I just use the a cube, a hydrogel cube, and stack 3 times at the same size and measure the stiffness. Okay, over here. So there is a video. So let me show you the stiffness measurement. See, so you can see this is the force sensor I used, and then when the force sensor plate attached on the hydrogel, I will get the data point like this way, a decay, right? So I can collect the data point from here to here. So I will have I will be able to analyze the stiffness of this hydrogel. So for the diffusion calculation, because I tried 3 different conditions: 1 minute exposure, 3 minutes exposure, and 5 minutes exposure. So because of the time, my presentation, because the time is very limited, so I just show you the final result. So for the 1 minute, I get the result is around 9 times 10 8 powers for the diffusion coefficient. And as you can see at 5 minutes, the diffusion coefficient is less than the 1 minute. So that means at the 5 minutes exposure time, the nanoparticle transport slower than the 3 minutes and 1 minute. And then also I calculate the Young's modulus under the different conditions on a 3 different timeline. So you can see the Young's modulus increase with the exposure time increase as well. So generally speaking, for the hydrogel I'm using, the Young's modulus is around 10, 10 or something. So it's very similar over here. So the stiffness is very similar to our skin. So that's the diffusion versus the mechanical property. So you can see the diffusion is decreasing with the time increase. The diffusion, the stiffness is increasing with the time, and the diffusion, but the diffusion decrease with the time increasing. Also, in order to find the better result, I also try to integrate one page with a soft part and a stiffer part in one pillar. So the method I was using is just to use a cover, a, a, a silicon cover, black silicon cover, to apply silicon paper to cover the half of the pillar and get the different stiffer on one same pillar. Okay, so you can see on the left hand side, the material is softer than the right hand side. Absolutely, you can see more Florence particle diffused in the softer part. Okay, so in my research, we examined 40 nanometers polystyrene Florence nanoparticle diffusion in different exposure time. So the diffusion coefficient decreases with the increasing exposure time. So that's the first result we get from the data. And the second result is the mechanical property of the PEG hydrogel are characterized by a customized force sensor, and the more UV exposure time causes the hydrogel to become stiffer. Okay, so finally, the experimental result indicate that the physical property of the hydrogel are one of the main factors hindering the diffusion of the nanoparticle diffusion in the tissue. It provides us a new focus point for improving the efficiency of the nanoparticle carrier delivery. Okay, so that's pretty much for today. Thank you for your attention. This is my email address. If you guys have any questions, just send me the email, and I will be very happy to give you my answer. Thank you. Bye bye.